Section 1.8, Introduction to Linear Transformations. The set of all ordered n tuples of real numbers is denoted by the symbol Rn. The elements of Rn are called vectors and are denoted in boldface type. Ordered n tuples can be expressed as this ordered n tuple right over here, S1 through Sn, called the comma delimited form of a vector, or as the matrix, with the S1 through Sn entries, called the column vector form. For each I through 1 through n, let ei denote the vector in Rn with a 1 in the ith position and zeros elsewhere. In column form, these vectors are right over here. So e1 will be the one with the 1 in the first entry, e2 with 1 in the second entry, and so on, where en has a 1 in the nth entry. We call the vectors e1, e2 through en the standard basis vectors for Rn. They are termed basis vectors because all other vectors in Rn are expressible in exactly one way as a linear combination of them. For example, if x is the vector given by x1 through xn, then we can express x as x1 times e1 plus x2 times e2 and so on through xn times en. A function is a rule that associates with each element of a set A one and only one element in a set B. If f associates the element b with the element a, then we write b equals f of a, and we say that b is the image of a under f, and the set B is the codomain of f. The subset of the codomain that consists of all images of elements in the domain is called the range of f. If t is a function with domain Rn and codomain Rm, then we say that t is a transformation from Rn to Rm, or that t maps from Rn to Rm, which we denote by writing t from Rn to Rm. In the special case where m equals n, a transformation is sometimes called an operator in Rn. Suppose that we have the system of linear equations written in matrix notation as w equals ax, which we can view as a transformation that maps a vector x into Rn into the vector w in Rm by multiplying x on the left by a. We call this a matrix transformation, or matrix operator in the special case where m is equal to n. We denote it by ta from Rn to Rm. In situations where specifying that the domain and codomain is not essential, we will write w equals ta of x, and we will call the transformation ta multiplication by a. On occasion, we will find it convenient to express this in the schematic x with this little arrow over here to w, where we put the transformation above the arrow, which is read ta maps x into w. Let's do an example. How about we find the image of the vector x right over here under the transformation from r to 4 to r3, defined by the equations w1, w2, and w3. So how about we write out the column vector w, so w1, w2, w3, and we'll set that equal to the coefficient matrix right over here. So reading off those coefficients, we've got 2, minus 3, 1, minus 5, 4, 1, minus 2, 1, 5, minus 1, 4, 0, and we will multiply that by x1, x2, x3, and x4. This is the same thing as writing the vector w equals a times the vector x. So if we want to write the transformation, that would be ta of x. So that's given by a times x, which is this, again, this coefficient matrix, so that's 2, minus 3, 1, minus 5, 4, 1, minus 2, 1, 5, minus 1, 4, 0. And the x they gave us was 1, minus 3, 0, 2. So that's what we'll sub in over here. 1, minus 3, 0, 2. and we'll perform the multiplication, and we should get 1, 3, 8, which is the image of x under this transformation. Notice it takes you from 4 entries, R4, to 3 entries in R3. Let's find T0 of x for an arbitrary vector x in Rn. So remember, 0 is the m by n0 matrix. So T0 of x is just the 0 matrix applied to x. So that's just the 0 vector. So that means that it's always going to be the 0 vector. We call this the 0 transformation from Rn to Rm, because the image is always 0. Let's now find Ti of x for an arbitrary vector x in Rn. Remember, I is the n by n identity matrix. So Ti of x just applies I to x. So that means we just get x. Identity doesn't change it. We call that the identity operator on Rn. For every matrix A, the matrix transformation TA from Rn to Rm has the following properties for all vectors u and v, and for every scalar k. TA of 0 is 0. TA of a constant times u is the constant times transformation. You can just pull the constant out. TA of u plus v is TA of u plus TA of v, and TA of u minus v equals TA of u minus TA of v. T from Rn to Rm is a matrix transformation if and only if the following relationships hold for all vectors u and v and Rn and for every scalar k. The TA of a sum is the sum of the transformations, and the transformation of a constant times a vector is a constant times transformation. We call this linearity of the transformation. Let's prove this real quick. If T is a matrix transformation, then properties 1 and 2 follow respectively from parts C and B of this theorem right over here. So we just prove the other direction. So let's assume that we have these properties, and let's prove that it's a matrix transformation. So we'll have to show that there exists some matrix A such that T of x is A of x for every vector x in Rn. Let's use the additivity and homogeneity properties of T of A. That's this and this that we're assuming. So we'll get T of this constant times, or each of these constants. I'll do K1, K2 through Kr. We'll pull out each constant. And that's true for all scalars, all those constants, K1 through Kr, and all the vectors U1, U2 through Ur and Rn. All we have to do now is let A be the matrix that equals T of E1. Remember that standard basis vector we talked about that has a 1 in the first entry and then 0 for the rest of them. And then the next column will be T of E2 and so on. So it's a matrix formed of all of the standard basis vectors for Rn. So it starts with 1, and then it has a bunch of zeros, and then 0, and then 1, and a bunch of zeros, etc. A of x is a linear combination of all the columns of A in which the successive coefficients are the entries x1 through xn of x. That is, ax is equal to x1 times t1, x2 times t2, and so on. But we could just put the x's inside by linearity, because we're assuming the homogeneity property. That's the second property. So that's the same thing as saying it's the transformation of this thing. But that's just the transformation of x. So we found a matrix such that A of x is T of x. So that proves this actually is a matrix transformation. The additivity and homogeneity properties in theorem 1.8.2 are called linearity conditions, and a transformation that satisfies these conditions is called a linear transformation. Using this terminology, theorem 1.8.2 can be restated as follows. Every linear transformation from Rn to Rm is a matrix transformation, and conversely, every matrix transformation from Rn to Rm is a linear transformation. If TA from Rn to Rm and Tb from Rn to Rm are matrix transformations, and if TA of x equals Tb of x for every vector x in Rn, then A has to equal B. Basically, if we have transformations that have the same images, then they have to be using the same matrix. Okay, so let's prove that. To say that TA of x equals Tb of x for every vector in Rn is the same as saying that Ax equals Bx for every vector x in Rn. This will be true in particular if x is any of the standard basis vectors, e1 through en. So that means that it'll be true if we take ae of j equal to be of j for j1 through n. Since every entry of ej is 0 except for the jth, which is 1, it follows that aej is the jth column of A and bij is the jth column of B. Since aej equals bij, this implies that the corresponding columns of A and B are the same, and hence that A equals B. Theorem 1.8.4 tells us that every m by n matrix A produces exactly one matrix transformation, multiplication by A, and every matrix transformation from Rn to Rm arises from exactly one m by n matrix. We call that matrix the standard matrix for the transformation. So there are just two steps defining the standard matrix for a matrix transformation, the first of which is let's find the images of the standard basis vectors, e1, e2 through en, similar to our proof, and we'll construct the matrix that has the images obtained in step 1 as its successive columns. Then this matrix is the standard matrix of the transformation. So as an example, let's find the standard matrix A for the linear transformation T from R2 to R2 defined by this formula that we have right here. So first we need to take T applied to E1, which is going to be T applied to the matrix 1, 0. That's E1. So that's, let's see, we plug in 1, we plug in 0 over here. We get 2 plus 0 is just 2. We get 1 minus 0 is just 1. And we get minus 1. Let's also get T of E2 because we're in R2. So we have two standard basis vectors. So that's T applied to 0, 1. Okay, so now all of these are 0. And all of these are 1. So we get 1 minus 3, 1 it looks like. Okay, so now we'll form the matrix A by taking T of E1 and T of E2, just like in our proof. So the first column is 2, 1, minus 1, that's this guy. And our second column is 1, minus 3, 1. This means that A applied to x1, x2 is 2, 1, 1 minus 3, minus 1, 1 applied to x1, x2 for this transformation. We could multiply that out and see that this transformation is in fact equal to 2x1 plus x2, x1 minus 3x2 minus x1 plus x2, which is in fact the transformation that we were given. So the matrix does match up. For the linear transformation in example 4, use the standard matrix A obtained in that example to find T of 1, 4. Okay, so let's do a t of 1, 4. So that should be equal to 2, 1, 1 minus 3 minus 1, 1. That's on my matrix A. I'll apply that to the vector 1, 4. And I'll get 6 minus 11, 3, once I do the multiplication. How about we rewrite the transformation t of x1, x2 equals 3x1 plus x2, 2x1 minus 4x2 in column vector form and find its standard matrix. So we'll take t of x1, x2 equals 3x1 plus x2, 2x1 minus 4x2. I'll write that as a matrix. Okay, so that's the same thing as saying it's 3, 1, 2 minus 4 times x1, x2. You can basically just read off the coefficients to get A. So that means that A is 3, 1, 2 minus 4. Let's find the standard matrix A for the linear transformation from R2 to R2, for which t of minus 1, 1 is minus 5, 5, and t of 2 minus 1 is 7, minus 6. Okay, so first, how about we write our standard basis vectors as a linear combination of these vectors over here that we're given. Because we're given these vectors in an example, but we're not given the explicit transformation. So we'll take 1, 0, and we'll write that as some linear combination of minus 1, 1 and 2 minus 1. So we'll say, we don't know what constant has to fit in yet, but we'll figure it out. But it'll be something times minus 1, 1 plus something times 2 minus 1. And similarly, for my other standard basis vector, because we're in R2, there's only one other one, it's 0, 1. It would have to be some other constant. Let's say k1 times minus 1, 1, and k2 times 2 minus 1. Okay, so I could write this as matrix minus 1, 2, 1, minus 1 times c1, c2. And I know that has to equal 1, 0. And I know similarly over here, minus 1, 2, 1, minus 1 times c1, c2 has to equal 0, 1. So now I need to figure out what c1 and c2 are, so let's write minus 1, 2, 1, minus 1, and I'll put 1, 0, and while I'm at it, I'll put 0, 1, because I could just solve for both at once, because both of these matrices are the same. Oh, I made a little mistake over here. I wrote C1 and C2, but I'm already using those on the other side. It's be K1, K2. Okay, so then let's solve this, and we can solve for both constants at the same time. We'll solve for C1, C2, and K1, K2. Okay, so we have 1 minus 2. If I multiply the top row by minus 1 to get a leading 1 over there, so that means I get minus 1 and 0. And I'll leave the bottom row the same. I would like to get a 0 underneath now, so I'll leave the top row the same. But for the bottom row, I'll subtract the top row from that. I'll get 0, 1, 1, 1. Okay, this means that I could just add 2 of the bottom row to the top row. So I'll get 1, 0, 1, 2, and my bottom row is 0, 1, 1, 1. So the left is the identity, so it looks like we have C1 equals 1, C2 equals 1. And it looks like we have K1 is 2 and K2 is 1. Okay, so that means that the transformation applied to the vector 1, 0 is the transformation applied to minus 1, 1 plus the transformation applied to the vector 2, minus 1. Because if I plug in 1 and 1 over here, then that means that 1, 0 is the 1 times this plus 1 times this. So that means that if I apply the transformation, then the transformation will have that same constant. So this is just minus 5, 5, plus 7, minus 6. And that's just 2 minus 1. This is why it's so nice to have homogeneity, being able to pull constants in and outside of transformations. Let's look at t of 0, 1. So that's, well, k was 2 for that one. So that means I'm going to have a 2 over here. 2 times t of minus 1, 1. And 1 of t of 2 minus 1. Okay, so that's minus 10, 10. Plus 7 minus 6. And that's minus 3, 4. So I was able to take just the fact that t of minus 1, 1 is minus 5, 5, and the fact that t of 2 minus 1 is 7 minus 6, and I was able to extrapolate the effect of the transformation on my standard basis vectors 1, 0 and 0, 1. So putting these results together, I figure out that the matrix is 2 minus 1 and minus 3, 4 for my other one. Because we figured out what happens to our standard basis vectors. That's what gives us the A, our matrix for a transformation. So that means that, well, we could always just double check. T of minus 1, 1 should be 2 minus 3 minus 1, 4 times minus 1, 1 if we have the correct matrix for the transformation. And we get minus 5, 5. So it worked for that. Let's look at t of 2 minus 1. So that's 2 minus 3 minus 1, 4. Multiply that by 2 minus 1 this time, and we do get 7 minus 6. Alright, so that's great. Some of the most basic operators in R2 and R3 are those that map each point into its symmetric image about a fixed line or a fixed plane that contains the origin. These are called reflection operators. Matrix operators in R2 that move points along arcs or circles centered at the origin are called rotation operators. So let's talk about a couple of different operators. If we want to reflect about the x-axis, so we're taking a point over here, we're reflecting it so that it pops out over there, using some transformation, then you might have learned that that transformation is given by the coordinates x minus y if you started with xy. But using transformation terminology, that means that it takes the standard basis vector e1 and standard basis vector e2, and it sends them to 1, 0, and 0, minus 1. So that means that we get the standard matrix formed by those 1, 0, and 0, minus 1. So that means that we could take a vector x, we could multiply it by the standard matrix 1, 0, 0, minus 1, and it would end up being reflected over the x-axis in R2. Similarly, if we wanted to reflect about the y-axis, we'd multiply by the matrix minus 1, 0, 0, minus 1. If we wanted to reflect about the line y equals x, we would swap x and y. So that means that 1, 0 becomes 0, 1, 0, 1 becomes 1, 0. So we just multiply by the matrix 0, 1, 1, 0. We can also apply this to 3 dimensions. In that case, we would be taking xyz to xy minus z if we wanted to reflect about the xy plane. So here's the xy plane. It's this piece over here, but it extends infinitely. And if we wanted to reflect over that, then 1, 0, 0 will still get sent to 1, 0, 0. But and 0, 1, 0 still gets sent to 0, 1, 0 because x and y still get sent to x and y, but z is what gets flipped because we're reflecting over. So 0, 0, 1 goes to 0, 0, minus 1. So all we get is a minus 1. Otherwise, it's the identity. And this is pretty similar depending on which plane. If you want to reflect over the xz plane, then the minus 1 is in the middle. And if you want to reflect about the yz plane, then the minus 1 is in the top left. Again, pretty similar to what we had in R2 for the reflections. The minus just showed where you were reflecting. We can also describe orthogonal projections using transformations and matrices. So if we wanted to project off of a vector straight down onto the x-axis, then we're just taking x and leaving it alone, but we're taking whatever y value is and we're just making it 0, going straight down. So that means that x stays the same, so we still have 1, 0, but we put in a 0 for the y. Similarly, if we wanted to orthogonally project onto the y-axis, then we leave y the same and x becomes 0. And that's reflected in our matrix. If we want to orthogonally project onto the xy plane in R3, then pretty similar. Z becomes 0. So you get a 0 over there for z. If you want to go onto the xz plane, you make y 0, put in a 0 for y. And if you want to orthogonally project onto the yz plane, you make x 0, put in a 0 for x. Last but not least, we have the counterclockwise rotation about the origin through an angle theta. Notice that if we take the transformation and apply it to E1, we get cosine theta sine theta, and applied to E2, we get minus sine theta cosine theta. This might be a little bit hard to see at first glance. However, it's not too surprising. If you take, for example, E1, it could be right over here, have length 1. Let's say you rotate it up by an angle theta. So then what I could do is I could draw a triangle. This has length 1. This angle in the triangle is theta. So the bottom piece is the adjacent divided by hypotenuse. So the bottom piece would have to be cosine, right? Because cosine of theta would be the adjacent piece in the bottom divided by the hypotenuse is 1. So let's say I made it x on the bottom. That means cosine of theta is equal to x over 1. So cosine theta is x. Similarly, we could figure out that sine theta is that opposite side. So the vector E1 would be transformed into cosine theta sine theta. Similarly, if we looked at the vector E2, that's the vector 0, 1. And if that rotated by an angle theta, then again I can draw a little triangle. I can see that this piece over here will be opposite, so that's sine theta, that's 1 over here, so this adjacent piece is cosine. Notice if I want to write the coordinates, the x-coordinate is negative in this quadrant, so that's minus sine theta. The y-coordinate would be cosine theta, and it makes sense that we'd have minus sine theta, cosine theta for that. So we get this is the transformed E1, this is the transformed E2, and it makes sense that this is our standard matrix for counterclockwise rotation. As an example, let's find the image of x under the rotation of pi over 6 radians about the origin. Oh, by the way, this is commonly referred to as r theta. This matrix is our standard rotation matrix. So let's take r theta for r pi over 6, and we'll apply that to x. And that means that we're taking cosine of pi over 6, which is square root of 3 over 2. We're going to take minus sine of pi over 6, so that's minus a half. And then sine of pi over 6 is a half. And then cosine of pi over 6 again is rad 3 over 2. So what we'll do is we'll apply that to 1, 1. And doing the multiplication, we get square root of 3 minus 1 over 2, and 1 plus square root of 3 over 2, which is roughly 0.37, 1.37. So that means we could say that r pi over 6 of 1, 1 is about 0.37, 1.37.